For the remaining examples, we'll focus on just simplifying radicals. And the prior lessons that we've learned on simplifying radicals still apply here whenever we're dealing with nth roots. Now, you may notice one thing here in this first section, that when we have an even value for the root, when we were solving for the x variable, we would use the plus or minus sign. So if we had something to this situation here, if we took the fourth root of both sides, in this case we would need to use the plus or minus sign. Now, if we're just simplifying radicals in this case and we're not solving, then we're just going to worry about the positive, and that's where that absolute value of a comes into play. That's just giving us the absolute value of the given root. And so you no longer need to worry about the positive plus or minus sign if we're simplifying radicals. So we'll focus the rest of this lesson and sample problems on simplifying radicals. And of course the same properties that we had used before with square roots still apply here. We can break them up through multiplication, or we can combine them back together through multiplication, and the same thing through division. Now, you do want to be careful of rationalization of a root value greater than 2. It's a little different than what we've done in the past. So if you look at the examples, I'll point out particularly part D. In part D, this 8 over 8 is the rationalization of the radical, and the reason being is because we wanted to get a perfect fifth root in the bottom, and the fifth root of 32 is 2, and that's helped us rationalize the denominator. So let's go ahead and, if you haven't tried yet, give sample problem 2 a try, and then come back and look at the answers. Okay, for part A, we basically have here a simple calculator function. If you're not familiar with your cubed roots yet, you could use your calculator on this, but basically what we have is 4 to the third power, which is 64, and this allows us to cancel out the 3's, leaving us just 4. So that's a very simple problem, and of course you could punch that straight in your calculator and it would give you the answer right straight away. On part B, we have it broken apart, and neither one of those are perfect cubes, but by putting them together through multiplication, we can do the cubed root of 125, and 125 does have a perfect cube in it, which is simply 5. Alright, in this last one, we can break the division up, and we can have the fourth root of 7 over the fourth root of 8. Now this is where we have to rationalize the denominator. If we were doing square roots, we would probably use the square root of 8 again to eliminate that, but that will not work with degrees higher than 2. So what we really need to do is figure out, and this is how you can kind of work backwards. We're going to be multiplying by some fourth root here. Ultimately, I need the fourth root here that is a perfect fourth root, so that I can take that out of the radical. So what I really need to do is figure out, if I multiply something times 8, what can I get that'll be a perfect fourth root? Now, there are tons of multiples that you could do that way, but we really want to look for the smallest one, the least common denominator that would work. And in this case, the least common denominator would be 16. So the fourth root of 16 is actually going to give us 2. So in order to get to 16, I really need to multiply this by the fourth root of 2. And in the rationalizing process, I have to do the same on top. Now, that's going to give me the fourth root of 14 on top. What this gives me is the fourth root of 14, which there are no perfect fourth roots. But the fourth root of 16 is 2, and I no longer have the radical in the denominator. And that was what I was looking for. So that is an example that you need to practice and work with in rationalizing the denominator. That'll be a very important skill for you to learn. Alright, that's it for this sample.